am Dr. Ramanuja, working as Associate Professor in Department of Mathematics, Marri Laxman Reddy Institute of Technology and Management, Dundigal, Hyderabad. This is the first module of this course about mean value theorems and also Taylor series expansions and also special function. In this module, I am going to cover. Let us go with the briefly about the course description. In this one, first one, I am going to discuss about 3.1 module, Rolle's theorem and their geometrical interpretation. And also 3.2, I am going to discuss about the Lagrange's mean value theorem and their geometrical representation with an example problems I am going to discuss. And 3.3 module, I am going to discuss about the Cauchy's mean value theorem and their related to the problems. And also in 3.4 module, I am going to discuss about Taylor series of expansion as well as the Mlritm series of expansions. And 3.5 module, I am going to cover beta gamma function, which is a special functions. In this module, I am going to cover all the content 3.1 modules of 3.2, 3.3 and 3.4 and 3.5. First, I am going to introduce. First, I am going to talk about the Rolle's theorem statement and how the existence of the Rolle's theorem for the any function for single functions. Let us go with the definition of the Rolle's theorem statement. Let f is a function such that defined from the closed interval ab to real number r. F is a function defined from closed interval ab to r. And also the first condition shows the Rolle's theorem, f is a continuous in the closed interval a comma b. F is a continuous in the closed interval a comma b. And the second condition, f is a differentiable in the open interval a comma b. And also in 3.3 condition, f of a value equal to f of b, there exists a point c between a and b such that f dash of c equal to 0. This is the statement about the Rolle's theorem. For this course, I am going to refer the textbooks like Higher Engineering Mathematics and B.S. Gravel and J.C. Jain, and also some parts I am going to refer the textbook like A.S. Chand. Okay. In this Rolle's theorem statement, I am going to write in the geometrical representation. Let us take the function along the xy plane. Let's take the function xy plane. In this plane, what first one says already about the continuous function. Already you familiarized by the continuous functions. Let us take the continuous function polynomial functions. Polynomial functions always are continuous in the given certain intervals. And also trigonometric functions is also a continuous in the closed intervals. And also exponential functions is also a continuous function. Already you previously you have idea about the continuous functions. And also differentiability also you have idea. Let us take the continuous functions, and if any function which is a continuous in the closed interval a comma b and f is a differentiable open interval a comma b, there exists f of a equal to f of b. Let us take x equal to a on the x-axis, x equal to b on the y-axis. At this particular points a comma b, at the particular point a comma b, f of a value, f of b values are equal. F of a value equal to f of b. If they are equal, this is a continuous, they are equal, they in between there exists a point c. There exists a point c. If there exists a point c, at this particular point, there f dash of c value is always 0. F dash of c value is 0. Suppose at this particular point, I can draw a tangent. This tangent is parallel to this chord and also this tangent is parallel to the x-axis. This tangent is parallel to the x-axis. This is the geometrical representation of the Rolle's theorem. What is the statement? F is a function defined from the closed interval a comma b to r and which is a continuous function in the closed interval a b. F is a differentiable in the open interval a b and f of a value f of b are equal. We observed in this case I can say a comma f of a value b comma f of b values always equal. If both are the equal, there exists a point c, there exists a point C in between A comma B, that particular point when we draw a tangent, f dash of C value equal to what? 0. Therefore, f dash of C equal to 0. This is the statement about the Rolle's theorem. Further, we are going to extend this in the geometrical representation of the function. Now, we are observing how the existence of the geometry of the Rolle's theorem. Let us take this curve. There is a open upward curve and downward curve we are observing in this case. This curve is always a continuous. And at this particular point, x equal to a value, f of a value, both are equal. And x equal to b, f of b value also equal. In this case, f of a value equal to f of b. I can join the chord of these two curves. At this particular point, there exists a point C between A and B. There f dash of C equal to how much? 0. F dash of C equal to 0. Let us take the open upward curve. In this case, f of A value, x equal to A. In this case, x is equal to B. F of A value as well as f of B values are equal. When we take the point C in between A and B, there exists a point C, f dash of C exists, f dash of C equal to how much? 0. When we draw a tangent to this curve, this tangent to the curve is parallel to this chord as well as the parallel to the x-axis. This is the geometrical representation of the Rolle's theorem. Let us look the first condition what it says, y equal to f of x is a continuous function. Whenever we define the function, this function must be a continuous. And also there exists a unique tangent, we draw a unique tangent to the where we drawn tangent at the particular point of C, that C value is always lies between A and B. This is a condition to existence of the Rolle's theorem. In that case, whatever we calculated the ordinate values, f of A values and f of B values must be equal. F of A value, f of B value must be equal. When there is a equal, at least one point C between A and B to the curve tangent to the parallel to the tangent as well as parallel to the chord as well as parallel to the x-axis. This is the geometrical representation of the Rolle's theorem. Let us go with the example problem. We will apply this example problem to the Rolle's theorem. Okay, verify Rolle's theorem for the function f of x equal to x square minus 2x in closed interval 0, 2. Already you know the given function is a polynomial function. The polynomial function is a continuous function, and we need to calculate the point C. That point C between where? In between 0, 2. Okay, let us solve this problem. Let the given function f of x equal to what? X square minus 2x. Already we know this is a polynomial function. This polynomial function is a continuous function. In between where? In between 0, 2. f of x is continuous on closed interval 0, 2. F of x is a continuous on closed interval 0, 2. And also f of x is differentiable on open interval 0, 2. Already we know the third condition, both f of A value, f of B value must be equal. Let us take f of x value. What is f of x? F of x equal to x square minus 2x. What is A in this case? A value is 0 as well as B value is 2. Let us substitute A value is 0 in this polynomial function, 0 square minus 2 into 0, the resultant value is 0. And similarly, we need to substitute B value. B value is how much? 2. F of 2 equal to what? 2 square minus 2 into 2. What happens? 2 square means 4. 4 minus 4. This also 0. What we observed, f of 0 value is equal to f of 2. This is the third condition. If both values are equal, there exists a point C belongs to open interval 0, 2. Wherever there is a point C, that point between 0 and 2. We need to calculate C value. C value is always lies between where? 0, 2. Okay. For this case, wherever, because f of 0 value means what? Ordinate values. Ordinate values are equal. Then there we need to calculate the derivative. F dash, what is f dash of x for this function? What is x square derivative? 2x minus, what is the derivative of 2x? 2. Put x is replaced by c, this becomes f dash of c, which is equal to 2c minus 2 equal to 0. Therefore, f dash of c equal to 0, 2c minus 2 equal to 0, 2c equal to 2, c equal to 1. See, we got the value of c. This c value is always lies between where to where? 0 and 2. Therefore, C belongs to open interval 0, 2. We take these interval values, we take in between 0, 2, C equal to 1 in between A and B. Therefore, this function satisfies the Rolle's theorem. What is the statement? One is continuous function, second one is differentiability, and third condition is f of A equal to f of B, and also f dash of c is equal to 0 at this particular point of c, that c value is lies between the open interval a comma b. This is the condition about the Rolle's theorem. Let us go with the second example problem in the Rolle's theorem. Verify the Rolle's theorem for the function f of x is equal to sin x by e power x in between 0, pi. Okay, look this function f of x. What is f of x function? F of x equal to what? Sin x by e power x. Already you familiarized by the functions of sin x function. Sin x functions are always a continuous functions, as well as exponential functions is also a continuous function. If you take the f of x function as a sin x, g of x function is a e power x, f of x by g of x functions is always a continuous function in the given certain domains of real number system. Now, f of x by sin x, I can say f of x is continuous on closed interval 0, pi. F of x is a continuous on closed interval 0, pi, as well as f of x is differentiable on open interval 0, pi. F is a differentiable on open interval 0, pi. What the second condition shows? F of a value equal to f of b. Let us take a value is 0 and b value is pi. Now, I am going to substitute a values as well as b values for this function. F of x is equal to sin x by e power x. F of, I am going to substitute a is 0, therefore sin 0 by e power 0. Already you know sin 0 is 0, e power 0 is 1, therefore 0 by 1 which is always a 0. And the second condition, we need to substitute b value. B value is how much? Pi. Therefore, f of pi is equal to sin pi divided by e power pi. Already we know sin pi value is 0, e power pi is having some decimal number. When we divide 0 by some decimal number, this resultant value is also 0. What we observed from this case, f of a value, what is f of a value? 0, and f of b, what is b value is pi, both having equal values. F of a value equal to f of b value. In this case, there exists a point C between the open interval 0, pi. Whenever we take the interval values, from 0 to pi, at least one point lies between a 0, pi. Let us go with there. We need to, for this case, we need to calculate the derivative. Okay, let us take f of x value. What is f of x? Sin x by e power x. I can rewrite this function. I can calculate the derivative by two procedures. One may applying u by v formula, or one function you can apply u into v formula. Let us take f of x is equal to e power minus x into sin x. I can rewrite the denominator function, I can move towards up, it becomes negative sign. For this case, I need to calculate the derivative. I am going to apply u into v formulae. Therefore, f dash of x is equal to, I need to calculate u into v formula. What is the derivative of u into v? U into derivative of v plus v into derivative of u. Let us assume e power minus x, I am going to keep first as a constant, derivative of sin x, this becomes cos x, plus I am going to keep sin x as a constant, I can make the derivative of e power minus x. What is the derivative of e power minus x? Minus e power minus x. In this case, I calculated the derivative by applying u into v formula. Then I am going to substitute x is replaced by what? C. Therefore, f dash of c is equal to e power c into cos c minus sin x sin c into e power minus c. What Rolle's theorem says? F dash of c value is how much? 0. If this left hand side is 0, I can take e power minus c is common, the resultant becomes cos c minus sin c. Already we know e power minus c never 0, but this trigonometric function is equal to 0. What happens now? This becomes cos c minus sin c equal to 0. This is nothing but cos c is equal to sin c. 1 is equal to sin c by cos c. Therefore, tan c is equal to 1. Tan c is equal to how much? 1. Therefore, c is equal to tan inverse of 1. How do you write this one? C is equal to tan inverse of tan pi by 4. Therefore, tan inverse of tan, the resultant value is pi by 4. What is C value? C value I got pi by 4. What is the given interval? What is the given interval for us? It is 0 to pi. 0 to pi, which is 0 to 180 degrees. But how much we got C value? C equal to how much? Pi by 4. Therefore, pi by 4 value, C equal to pi by 4 value lies between 0 comma pi by 4. Therefore, Rolle's theorem is verified. Therefore, C value is always lies between 0 comma pi. This is the example problem based on the Rolle's theorem. Further, I am going to extend one more problem by applying the Rolle's theorem. Okay. For this problem, verify the Rolle's theorem for the function f of x equal to log of x square plus ab divided by x into a plus b in the closed interval a comma b, where a is greater than 0 and b is greater than 0. Okay, I am going to apply the Rolle's theorem for this function. Already you familiarized by the logarithmic functions. Logarithmic functions is always a continuous function with a certain domain in the interval values. Okay, let us take the f of function. What is the function? F of x equal to log of x square plus ab whole divided by x into a plus b. X into a plus b. This function, I am assuming instead of log of this entire function, I can use f of x. Therefore, f of x is continuous on closed interval a comma b. F of x is a continuous on closed interval a comma b, as well as f of x is differentiable on open interval a comma b. What we need to calculate the third condition, both value, whenever we substituted a value, whenever we substituted b value, both values must be equal in this case. What is a in this case? A itself, b is also fixed values now. Okay, let us simplify this function. F of x is equal to log of x square plus ab whole divided by x into a plus b. Now I am going to substitute x is replaced by a. Therefore, this becomes f of a. F of a equal to log of a square plus ab whole divided by, this x is replaced by a. If I multiply this one, this becomes a square, this becomes ab. What is the resultant value? This resultant value becomes 1. Therefore, log 1. What is log 1 value? Is 0. Similarly, we need to substitute f of b value. what is f of b value? Log of x is replaced by b. Therefore, b square plus ab whole divided by ab plus b square. What happens? Both, if you interchange these two values also the same, this becomes log 1. Log 1 is also how much? 0. Similarly, now what we proved now, f of a value is equal to f of b value. Both cases are the same. Whenever both a and b values are equal, there exists a point C, that C point belongs to the open interval a comma b. Whenever there is a point C, a comma b, that C value is always lies between a and b. We need to prove the fourth condition. Let us go with their derivative. I can rewrite f of x is equal to log of x square plus ab. I can simplify this function minus, I am going to apply log a by b, log of x into a plus b. If I calculate the derivative, f dash of x, what is the derivative of log x derivative? 1 by x, but there is a log of x square plus ab. I can simplify this one, 1 by x square plus ab. The derivative of x square, what is the derivative of x square? 2x minus the derivative of log x. Here also the same derivative log x is 1 by x. Therefore, 1 by a plus b. Log x derivative is 1 by x. X is nothing but 1 by a plus b into inner derivative of the function. What is the inner derivative of the function? A plus b. Inner derivative of the function a plus b. Now, what is log x derivative? 1 by x. Inner derivative x square derivative is 2x, ab derivative is 0. Here is log x derivative is 1 by ab, x derivative is a, x derivative is b. Okay, we need to substitute C. In this case, we need to substitute, put x is replaced by C. What happens? F dash of C is equal to 2c divided by c square plus ab minus inner derivative of this function. This will be gets cancelled. This is nothing but what? 1. Is nothing but 1. Then f dash of c value is how much? F dash of c equal to 0, which is nothing but what? 2c divided by c square plus c square plus ab minus 1 equal to 0. X square derivative is 2x, ab inner derivative of the function. Therefore, 2c is equal to 2c divided by c square plus ab equal to 1. What happens? C square is equal to ab, c equal to root ab. Therefore, the c value always lies between a and b. Okay, this is the example 3 problem. We'll go with the example 4th problem. Here, in this case, verify the Rolle's theorem for the function f of x is equal to x minus a whole power m, x minus b whole power n, where m and n are the positive integer values in the closed interval a comma b. Here, in this case, already we know x minus a. There we taken as a m and n are the positive integer values. M and n are the positive integer values in the closed interval a comma b. I can use m, n are the 1, 1. I can calculate the polynomial function. I can substitute m, n are different values. I can calculate the polynomial function. This polynomial function is a continuous function. Polynomial function is a continuous function in the closed interval a comma b. Okay, let us go with the statement. Verify the Rolle's theorem for the function f of x equal to x minus a whole power m into x minus b whole power n, where m and n are the positive integer values in the closed interval a comma b. Let us take the statement f of x equal to x minus a whole power m, x minus b whole power n. This function this is the function, let us assume this function f of x is continuous in the closed interval a comma b. F of x is differentiable in open interval a comma b. This is second condition. Third condition, we need to substitute a is always a and b is always b. We need to calculate f of a value. What is f of x? F of x equal to x minus a whole power m, x minus b whole power n. Now we need to substitute, put x is replaced by a, f of a, this becomes a minus a whole power m into a minus b whole power n. What is a minus a? Is 0. 0 times this one is 0. F of a value becomes 0. Similarly, we need to substitute f of b value. What is b value itself? It is b. F of b equal to, I am going to substitute x is replaced by b, therefore b minus a whole power m into b minus b whole power n. What is b minus b value? Is 0. 0 times this one is 0. F of b value also becomes 0. What we observed in this case, f of a value equal to f of b. We observed f of a equal to f of b. What the third condition? There exists a point C, that C point is lies between a and b. C value lies between a and b. We will take these interval values of a comma b, the point C in between a and b. Let us go with the derivative of this function. F of x is equal to x minus a whole power m minus 1 into x minus b whole power n. We need to calculate the derivative of this function. For calculating the derivative of the function, I am going to apply u into v formula. Therefore, f dash of x is equal to, I am going to keep x minus a whole power m as a constant. I can calculate the derivative. N is common, n into x minus b whole power n minus 1. Inner derivative of the function is 1 plus. Similarly, I am going to keep constant x minus b whole power n. Derivative is m x minus a whole power m minus 1. For this function, I am going to take the common. For this function, I am going to take the common. F dash of c is equal, I can substitute c also afterwards. F dash of c is equal to, I can take common x minus a whole power m minus 1. I can take the common x minus b whole power n minus 1. What will be the remaining? Here is x minus b whole power n is common. The remaining term is x minus a into n plus. Here is x power m minus 1 is common. The remaining term is m into x minus b. Okay. Now, I am going to substitute, put x is replaced by c. F dash of c is equal to c minus a whole power m minus 1, c minus b whole power n minus 1 into c minus a into n plus m into c minus b. Okay. What is f dash of c value? F dash of c value equal to how much? 0. F dash of c equal to 0. Therefore, c minus a whole power m minus 1 into c minus b whole power n minus 1 into n into c minus n into a plus m into c minus m into b. This is never 0, but this value equal to 0. This c minus a whole power m minus 1 never 0, c minus b whole power n minus 1 is never 0, but this value becomes what? 0. Now look, this quantity becomes, what is remaining? Nc minus Na plus Mc minus Mb is equal to how much? 0. Now we are going to separate all the variables. Now this becomes c is common, which is c is common m plus n, which is equal to, if it goes left right side, this becomes Na plus Mb. C is equal to NA m into B whole divided by m plus n. I got the value of C. The C value always lies between m into B plus n into A divided by m plus n. This is the Rolle's theorem verified in this case. Let us go briefly about the statement and what is the statement of the Rolle's theorem. First, we need to verify continuous function. First condition. Second condition is differentiable in the open interval and both f of a value equal to f of b. We need to verify. Always there exists a point C between the open interval. We need to calculate f dash of C is 0. We need to calculate which value C. Okay, this is about the Rolle's theorem. This is 3.1 module. Thank you.